You're all using descriptions instead of the, basically, you're describing it instead of defining it. Or I should say you're describing it instead of proving it. It's a whole. Well, I mean, good. But how is it discontinuous? You should be using the definition, right? Not just stating it's a whole, it's a jump, it's a vertical asymptote, it's a hole with a removed point. Okay? So, what these little parts are up above is what specific part of the definition it fails. Because definition of continuous, what does it take to have a discontinuity is for one of these to fail, one of these to be not true. At least one of those. Could be all three. At least one of those, which could be summarized, almost said surmised, summarized in this last statement. Yeah? So why do I say f of c with a little x? F of c is not defined. Why do I say the limit as x approaches c of f of x with a little x? The limit does not exist as x approaches c. Why do I have the point with a check but the limit with an x? The limit does not exist. Wait a minute, but the limit's infinity. Yeah, but it's not a constant. For discontinuities, the limit has to be a constant, and they don't agree. So actually this one fails how many parts of the definition? 2 and 3, right? What about this one? It passes 1, it passes 2, it fails 3. The limit does exist, the point does exist, but they do not equal one another or agree. Good. And then this is just a quick little reminder of removable versus non-removable. However, let's also remind ourselves, what would happen if you plugged in a removable discontinuity? 0 over 0, keep going, right? 0 over 0s are wholes versus non-removable? Number over 0, good. Now specifically if you're talking about rational functions. If they're not rational, L'Hopital's. If they're not rational, if they're not fractions, that won't necessarily help us. But if they are rational, that will help us. That will. How many of these graphs, this is a question I asked AB today, because they have a similar first 2 slides. How many of these graphs are piecewise functions? Which ones? Second one, for sure. Fourth one, for sure. Pause. Before we think any further, what would the inequalities be for this one? Greater than or equal to C. And then less than C. What would the inequalities be for this one? X equals C. Ignore the smartboard being dumb. And what else? I mean, that would be for the intervals, if we were to do negative infinity to c and then c to infinity. But how do we show that? Yes. Because doesn't it look like the same function on either side? So they're going to say x not equals c. So for everything but c, this guy. And for everything, nothing but c, that guy. Right? In piecewise functions, which ones do I see you guys get most commonly confused on? This one. Yeah. What's going to be the inequality for this one? Wait, this one's a piecewise? It wouldn't be, except there's a, no natural vertical asymptote. It's going to have a point. What are the inequalities for that one? What kind of function could that be? 1 over x squared that's been shifted, so what? 1 over x plus c, x minus c, quantity squared, right? There you go. But that's not enough. That's enough for everything but the point. So what would the inequalities be? Good. X equals c and x not equals c. A few of you guys got it. Why am I saying this? Because you get stuck on these ones. X not equals c just means everything but that one little point, and that one little point is. These are the visuals for what that inequality means. Piecewises aren't that bad. You just aren't as familiar because you haven't seen them as long. Okay, are we good? For those of you guys who are needing to, I have not uploaded those forevers. When I get you guys going on new notes, I need to go update those forevers. What do I mean by that? In your guys' class folder, ESA, letters, I'm on it. Tomorrow, everybody gets their letters. I figured that'd be a fun Friday thing to do. Issa's been reminding me, like, have they gotten their letters from us yet? And I don't know why. My head just, I don't even know. But I have the letters, and they're ready to, I want to scan them first because I have fun scanning them, so that way I can read them. I've already read some. But you guys will get your BC letters, too, for better or worse. Hopefully it's for better. In your guys' CalcBC folder, oh, dear. Come on. Has anybody used Chromebooks yet this year? Yes. How quickly did they go? It was? Why is my computer slow? Class notes. What's normally in here, guys? The PDF copies, right? I'm also going to add in here, once I get you guys going on in notes, all of your forever cards from last year, and that's mostly for Sally and Daniel and Eric. That way you guys can go ahead and be making your forevers. We haven't talked about it a lot because kids from last year already have all of the CalcAB content in flip cards, something similar to this, where they can. Does anybody have their forevers on them? Oh, yes. That's from a few years ago. Why does he have two? Because one is for the forevers and one is for the endeavors. Now, we haven't done any CalcBC only topics yet, maybe polar parametric. But the forevers, why is it blank? No, because what did we do last year? Start from the back. That way you have the titles and you can go ahead and be like, oh, hey, did I get it right? And then the titles and like, oh, hey, did I get it right? And then the titles, oh, hey, did I get it right? That would have been cool though, huh? Anyway, I have the AB kids doing it this way this year. He did it on his own. But you have the titles on one side and then you can flip it and be like, yay, I got it right. Yay, I got it right. You can do it on your endeavors. Okay, so those of you guys that didn't have me last year, you're missing all of these. Why am I bringing that up? Kiddos, thanks, James. Why am I bringing up forever cards right now? Yeah, definition of continuous is one of those forevers. That's actually forever number 4? I think it's forever number 4. Intermediate value theorem is somewhere there close as well. So I'm going to pull that up into your guys' class folder. That way you guys can be working on, those of you that need to, can be working on making your forevers, and those of you that have your forevers, finding them, A, bringing them, B, and making sure you have them, C. Dun, 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 dun. Okay, ready, set, in your groups, go. Ready, set, in your groups, go. If you guys want to, you can go in your workspace. If you want to do it in your notes, that's okay too. Ready, set, and go. X equals 3 to remove the discontinuity. Someone tell me some way they got rid of x minus 3. Change what to x squared minus 9? You still have the plus or minus 3. Cheater. Why am I writing x minus 3 with something right now? How do I know it cancels out? How do you know it's removable discontinuity? Pause. How could you have known without your calculator? Ooh. How?
0 over 0. Because you cross out the x minus 3.
Okay, now hold on. Issa's looking here. Yes, you're going to be able to cross. Don't know what I did. No, this was squishing a button. One of these. V-sheet, no. Oh, yes. Oh.
The other way. Yeah. Wow, that's pretty cool. Too much. Go back. There we go. That's good enough.
This is like, you know, this
now her board is just going to be really all over. There's no hope in this board.
Okay. Okay, wait, pause. Issa was like cross out. Yeah, but you wouldn't know that unless I did it. So, shh. Aryan, what did you say? How do you know 0 over 0? Plug what in?
3.
Oh, so you guys could have just plugged in 3 and figured out 27 minus 21 minus 6 is really just 0? Oh, and then 0 times 0? So if 3 is making 0 over 0 removable, what's negative 3? Because negative 27 plus 7 minus 6 is not 0. That's how I knew to put my asymptote at negative 3 and my hole at positive 3. How did I know that I was supposed to come in? Well, that was kind of guessing. But how did I know this line? Something called a slanty or oblique asymptote, which always exists if you have 1 degree lower on the bottom than the top, and if you do long division, you find your slanty asymptote. Anyway, coming back. That was fun. Ah! Okay, coming back. It was y equals x, right? When you divide with the remainder of something, something, something. Nah. Okay. Sorry, that's what I was doing in my head, why it took me a second. Coming back. Who's this? Well, it has to be an x squared somebody, right? You could do guess and check. It might not be very fun. What's another way than guessing and checking if you know that x minus 3 has to go in because it's 0 over 0? Grouping is going to be nasty because of the cubed. So you don't want to do an x method and then split apart because you want to see what the squared was and the single. I would say divide, and you can either use long division but only with the x minus 3, or synthetic division with the x minus 3 because he's nice and easy. So either way, I'm going to do a quick synthetic just because it's faster and to remind you guys of how it works. You have 1 for the cube, 0 for the squared, negative 7 for the x, and negative 6. It's going to be, I was going to do the other way. Positive 3. Because you take the 0 and plug in. Way you add down. Bring down the 1, 3, 3, 9, 2, 6, 0. Booyah! X squared plus 3x plus 2. Now you can say, ha! Ha! It's removed. And that was the point. F of x is equal to x squared plus 3x plus 2 all over x plus 3. Well, it doesn't really help, but yeah, you could. To find those. Wait, that doesn't make sense. Did I mess up my signs at all? 3, 9, 2, 6. Subtracting is if you keep the same sign. But I switched it with the 0, so then you can just add down. It's faster. We could FOIL it out. It'd be minus 3x squared and plus 3x squared. No, it works. Plus 2 plus 1. There should be zeros at negative 2 and 1. Oh, it must. Did I not cross it correctly? Maybe this goes down. Oh, it does go down. Lo siento. Does it go hit the axis? Yeah. Okay, my sketch wasn't so hot. What else do we have? What's number 4 say? Show that x minus 3 is a factor of the numerator. Well, how can we show that x minus 3 is a factor of the numerator? 0 over 0. Well, we talked about it. We just didn't do it officially. It would have been 0 over 0. But a lot of you guys hadn't thought about it unless you had gotten down to number 4, right? Remove all the common factors. Now compute the limit as x goes to 3 of the reduced form. What does it mean by reduced form? Yeah, so the x squared plus 3x plus 2. Because didn't you literally reduce to remove the discontinuity? Right? That's not canceling. Canceling is going to 0. Reducing is going to 1. One of the most confused words in math. When we plug in, you get 20 over 6. And 20 over 6 reduces to be 10 over 3. So then at the very final step, it says, show that the extended function, extended function. Take the current function and extend it. There you go. This is the current function, right? The very beginning one that we were given, x squared minus 9. Why are they saying for all x except 3? Because they want to keep everything the same except for the whole. And what do you do? Fill the hole. How can you keep the hole? You extend it and say, he's filled. Well, they're just letting you know what the snazzy name of it is. The extended function otherwise known as the continuous extension, is making a function continuous. Ooh, hey, on AP questions, do they like piecewise functions that make things continuous? Ah, there's a name for it. Continuous extensions of the original function. So they were introducing it to a term, but also letting you know what's going on when you see the not equal to and equal to and what they could theoretically be doing. But, guys, how many ways are there to fill the hole? There's only one value to fill the hole. How many ways are there to not fill the hole? Infinitely many, which is why the AP question is almost always, find the value k such that the function is continuous. Kathy? Yeah. Does that make sense? So, new term, continuous extension. For the AP, they don't call it anything, they just do it a lot. A lot. With like 1s and 2s and 3s and what's true, which is true. Or find the value of A and B and K and C and I don't know. Right? Okay, so that was just to dig a little bit deeper into continuous functions, and for some of you that piecewise, any luck? Ugh, bummer. It's because someone's teaching in there this period, that's why she's not. That's not your fault.
I thought she wasn't there, and then I walked out, and I said, "You're really hard because I forgot to like."
Oh, yeah.
And then I like walked back in. Wait, walked back in. I was like, "I'm sorry." You were so nice.
We love you, Kathy. You're all right. Wasn't Mrs. Sass in there?
Yeah.
Curly hair? Yeah. It's all right. We're good. Totally done that before. Where do I do it? There's a place. Oh, I don't remember. Okay, a few technicalities since we're talking about technicalities with continuous extensions. Just kidding. Happy Thursday, and just you walk right out.
And then Miss Leon like corrected him. She was like, "Well, this is an AP chemistry course, so I don't think this is your classroom." It was so awkward.
Closed interval, you have to completely disregard everything below A and above B. Does that make sense? For a function to be continuous on a closed interval, you're completely disregarding below A and above B, which is why the definition just changes a little bit. It says you don't have to have a two-sided limit everywhere because there is an exception at A, just come from above, and at B, just come from below. So on this one, we can say this is a continuous function on its domain. You guys know the domain of square root of 81 minus x squared, right? What's the domain of the square root of 81 minus x squared? Yeah, less than 9. And greater than negative 9, right? So it's continuous on the closed interval. Why? Because the limit is two-sided approaching negative 9 and two-sided approaching existing 9? No, there's nothing on the left, nothing on the right. So we can't say he's continuous, but we can say he's continuous everywhere in his domain from negative 9 to 9, because whenever you're talking about continuity on a closed interval, the definition gets adjusted just a little bit, just by definition of a closed interval. That's just a technicality. It's not a huge deal, but it can be helpful every now and then, especially as we go to improper integrals. Ooh, second semester. Improper? Integrals with infinities or vertical asymptotes as bounds. Dun, dun, dun. Can infinite areas exist? Aryan.
So for this, so A and B do have to be like themselves, right?
Yes, but it's continuous as x approaches A from the positive. So that's only talking about the limit itself. So f of A has to exist, and then the limit from above has to agree.
So if A itself
No. That's part of the definition of continuous. F of A has to exist first, right? And then the limit is only a one-sided limit that has to agree. And then the other one, F of B, has to exist. But then the one-sided limit has to agree from below. Yeah. So that's what you'd have to prove if you were trying to show that's true for a certain function. Now for this guy, the direction says find the value of A such that, I'm just going to make it bigger so you guys can see. Find the value of A such that, basically, make the function continuous at x equals -1. Find the value of A such that this guy is continuous at -1. Now this isn't specifically a continuous extension because it's not one of those where the only problem was a hole that needs to be removed or defined. What word am I trying to say? Else? No. 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 No term for it that I can think of. This isn't a function that needed to be defined only at one point, aka it's not a not equal to and equal to function. Instead, this one, just by seeing the inequalities, can you guys tell it's two branches coming together? Okay, so two branches coming together, we want it to meet, and in order to have it meet, what do we need to do? And the notation would be the limit as x comes towards -1 from below, which would be below 4 minus x squared, right? Needs to equal f of -1, which needs to equal the limit as x approaches -1 from above, which would be ax squared plus 1. True? Using the above and the below, the inequalities to guide us as to which piece. And how do we take limits? Plug it in, so we have 4 minus -1 squared equals, isn't f of -1 the same thing as the limit as you approach -1 from above? Sweet, let's just go ahead and plug in a -1 squared. Now it's easy cheesy stuff as long as we don't make a mistake. A squiggly a equals 2. It's like your SpongeBob on your shirt, possibly.
I got the same answer.
How'd you do it?
I just set them equal to each other.
We were setting them equal to each other. The functions themselves, because that's how you solve the limit, as long as you did that such that x equals -1, it'll be okay. It's a shortcut trick to solving. But when you plug in, it works because that's how we take limits. Does that make sense? Yeah, Riley. Because of the or equal to. So we went ahead and just grouped these two together because we said, oh, they're the same thing. Yeah. Okay, what are we left with? IVT. And I think that's it. IVT. You know what was funny? What was I in? Pre-cal? Yeah, regular pre-cal, not even honors. I randomly started speaking in a British accent without realizing it. And they all just kind of like, it's like, yeah, it's in there somewhere. It was just like a statement. It wasn't even, I don't even know. But I paused and I apologized. I'm like, sorry, it just came out. I don't, okay.
It just came out of me.
No, I mentioned the whole, on mission trips, they just speak in British accents, and it just, I don't know, sorry.
We have basically the whole story to justify for it. Yeah, people, like, the other communities that go to some weird shit, for really weird.
But they end up wanting to join the group by the end. Yeah. You can put forever card number. Wait, why are we saying forever card number? Now, some of you need to write it out because you never know this one, so it's not bad practice. Why am I saying forever card number? For those of you guys that I was referring to just a second ago, I have loaded into your CalcBC class folder, class notes, all the forever cards from last year. Those of you that were here last year, they're all in here. We're up to, oh, we've done that one. Definition of continuous and intermediate value theorem. We're up through forever number 5. With polar parametric being an extra, we'll get something in the endeavors eventually. Problem is we cover them at the beginning of the year, then again at the end, a little bit in between. I kind of like the endeavors being nicely formatted, hence why we haven't done any yet. If f, who's f? A function, is continuous. Why? Because otherwise you have no guarantees. On the closed interval a to b. How come open intervals are tricky? And if k, a certain y value, oh, if he's y, he's in between f of a and f of b, then there exists at least one number c, he's an x, in between a to b, such that f of c equals k. Yeah, I agree. But they both have the idea of the theorem in the name. Mean value, average. Ooh, average rate equals instantaneous rate. Intermediate value. Ooh, intermediate, in between. For a continuous function, there is an x value that's going to map to every in-between y value. There is an x value that's going to have the function map to every in-between y value. Yeah, it's so hard. So how on earth are you supposed to do the example down below when it says, does IVT apply? If so, find C? You check to see if it's continuous. No! X cannot equal 1. Wait, what's the interval? Ah, 1's outside. It's good. It's continuous on the interval. Check. So if it's continuous, what? How do you find C? Plug in what? Plug in 6 equals and find the x value. It's not even as hard as MVT. Don't have to find derivatives or anything. Set equal to 6 and find the x. How? I don't know. Multiplying, getting to one side, factoring. You guys will play with it during homework. Homework, fully attempted tomorrow, 7 a.m. Come with questions. People need to update forever cards. Start doing that. Ready, set? Bye, guys. Oh, not me?